I do want... Okay, let's actually react to this. Let's see what we have in here. Common ground. This looks spicy. We can do this one. High level versus low level. Design example weapon system. Blueprints versus C++. Oh yeah. Okay, this is gonna be rough. By rough, I mean it's gonna take me like 2 hours because 47 minutes plus my reactor, I can stretch it out. I can stretch it out to 2 hours. So this is gonna be rough. But I think we can do it. This man seems like he's going into details. Okay, let's get into it.
Engine gives you multiple options for programming games. You can use C++, and you can also use Unreal's Blueprint system. Some of the differences between C++ and Blueprints are pretty self-evident. With C++, you're writing code using a general-purpose text-based programming language. Blueprints are more visual and more specifically tailored to higher-level game programming. You write code by stringing together graph nodes that represent events, control structures, and function calls, and you define your data and interfaces through in-editor dialogues, instead of having to write out definitions with precise syntax. But beyond those obvious differences, there are some more nuanced questions to ask yourself about how to approach making games in Unreal. It's not just, should I use C++ or should I...
It is, how can I combine them to do the best thing I can?
Use Blueprints. In fact, that's kind of a false premise. Unreal is designed in such a way that C++ and Blueprints are very complementary. So a better question would be, where does it make sense to use C++ and where does it make sense to use Blueprints? That's the question I'd like to examine in this video. Along the way, we'll look under the hood to get a better understanding of the performance trade-offs between Blueprints...
Oh, this is interesting. This is what I want to see. If I understood correctly, I heard it somewhere that Blueprints are actually more performant with Python, but of course more slower than C++, but I'm not sure if that tells you anything, if it's faster than Python, but yeah.
Script and native code. And we'll discuss some basic design principles.
Oh, this is the guy. Okay, subscribe to this guy. He has like let me actually find. I'm not even subscribed. Okay, this is my streaming account. Okay, on my main account I'm subscribed.
Unreal.
Okay, this guy. Look, I already watched like a bunch of his stuff. This video, so good. So what he did is basically break down visually. I think from like the start of the Unreal Engine to initializing like your objects, instancing stuff, going from like construction to begin play to event tick, whatever. He went through like each step of what happens when you click on the executable to when you click play to when you actually see the game and start playing the game. And he did a really good job. Let me show you. Okay, this thing. Like he goes like, you go from this guy to this guy, this activates, there is some stuff here, and then he leads you through everything. It was really good. And I'll be honest, you know, when you look at this, there is a lot of information. You probably forget like 95+% of the stuff, but just getting the feel of generally how things work is really good. I think I watched this video twice, but yeah, this guy is great. Which is not good for me because he's gonna probably have some really good points relating to Blueprints and C++. I'm just gonna shut up and watch, okay?
And get a sense of how a project is typically organized to make effective use of both. Finally, we'll wrap up with a look at some of the things that differentiate the two. But before we get to all that, I'd like to start by talking about some of the things that Blueprints and C++ have in common. If I have a custom actor type and I want it to spawn another actor when the game starts, here's what that might look like in C++.
Yeah. Okay, so this is my main point, and I think he's gonna say similar thing. Like, you kind of get the same thing in Blueprint, but it's like one node in like 2 seconds to do this. But in here you have to like do a bunch of stuff, instantiate stuff, vector, spawn, offset, location, whatever. Like, it's a lot.
And here's the same thing in Blueprints.
Okay, he made it a little bit more complicated, but for the spawn transform, you don't even have to do this crazy stuff. Wait, transform, location, what is he doing? Oh, okay. Not sure why he needs is valid here. I guess because of the collision handling, it might not spawn if it doesn't have a space. I guess, yeah, then you can put is valid here. But you can also just ignore this and then it's gonna spawn 100% of the time. Okay, it's a little bit more complicated when you add these transform offsets.
These two snippets might look pretty different, but they give us the exact same result. And that brings us to an important point. You might choose to implement an example like this in C++, or you might use blueprints. But either way, you're writing code. You may be writing that code without typing any actual syntax, but you're still dictating how a program is going to behave at runtime. And almost certainly you're going to be working within an established software framework, creating new classes, and defining how those classes behave and interact with each other. In other words, you're going to be dealing with software design. So let's talk a little bit about design.
Yeah, this is important one. So just learning like design patterns and stuff like that, it definitely helps you with blueprints. It's not like you can ignore any software like norms or ways of creating stuff. Like you still have to learn interfaces, inheritance, libraries, whatever, functions, variables, everything. So it's not like you can just get away from this because you're using blueprints. But yeah, it might be, I don't want to say it might be like even more important for blueprints, but it's probably as important as for C++ to consider are you going to use interfaces or inheritance or components or whatever to do a thing. Because that's mainly going to determine how flexible the thing you're making is and how performant it is and how clear it is, how easy it is to work with and stuff like that.
When you're considering a complex piece of software like a video game, it's helpful to think vertically. Usually your goal is to implement some complex, high-level functionality. The way you actually accomplish that is by breaking the problem down into more fundamental bits of functionality that can be implemented at a lower level. If your game needs to have a super cool rocket launcher that fires different kinds of projectiles, and those projectiles fly around and hit stuff and cause explosions, that's cool. But you can't just implement that out of nowhere. You have to build up from something. So your game design gives you a definition for what your high-level functionality needs to look like. And the engine, framework, or libraries that you're using give you a solid low-level foundation to build up from. Our design process as programmers, then, is about filling in all the missing details in between. So for a weapon system, we might start by defining a simple inheritance hierarchy to connect our final classes back down to the types provided by the engine.
Maybe.
Then we'd want to decide what each of our custom...
Yeah, so this is kind of basics of inheritance, but you also have to keep in mind, is my game small and I'm going to have just the 3 weapons, or am I going to have like 50 weapons? Because this can become very cumbersome to work with if you have like 50 weapons and then you have some stuff in here in the general weapon class, maybe like a range, or maybe some stuff that you don't really need. Maybe you have like melee attack or like just a blast, like AoE blast weapon or something. And yeah, it gets complicated. So this kind of where you determine kind of what design principles to use. Will you use inheritance for smaller projects? Probably okay, but when you go higher level or bigger projects, maybe you want to do like data assets in interfaces to kind of decouple stuff, so you can kind of not have a bunch of baggage that you are not using on the weapon, because there is like a bunch of classes that are pretty different from each other, but are still weapons, so you kind of have to use the weapon-based class.
Some classes should be responsible for how they need to interact with other objects in our game, and what underlying engine functionality they should leverage. For example, the base weapon class might handle input from the player, manage ammunition, determine whether to fire, and handle cooldowns. For running line traces or spawning projectiles, we might use specialized subclasses, one for instant hit weapons and one for projectile weapons. Our final concrete weapon classes would extend from there. Of course, inheritance isn't our only tool for breaking down problems. We can also use...
Yeah. So this kind of sounds based when you're starting out, but right now when I look at this, I'm like PTSD, like, what if our weapon is like a melee weapon? It's kind of not a hit scan, like you're not projecting, it's not like a projectile. It's more like you have like a collider on your weapon that you need to maybe sometimes activate trigger and see what is it overlapping with or whatever. And like then like it doesn't sit in here as neatly, so maybe you kind of have to have an exception for the melee weapons. And yeah, it gets kind of ugly with inheritance.
Use helper objects or spawn new actors, and we can use components to add composable bits of functionality. At every level, we're going to be using functionality that's implemented in the engine. To aim and fire our weapon, we'll use input and control functionality from the player pawn. For detecting whether we've hit something, we'll run line traces or handle collision events. To allow actors to respond when hit, we might use the built-in damage system. And at a very high level, we want to control how all these things look and sound, which means we'll be incorporating different assets to take advantage of the engine's rendering, animation, effects, and audio systems. With Unreal, we can implement any of these things in C++ or in Blueprints. Either way, we're leveraging the same underlying engine systems in pretty much the same way. So for a single feature in our final design, like a weapon, there's a wide range of questions that have to be answered at different levels of abstraction. From the very low level, like how do I get the memory I need to work with, to the very high level, like what shade of purple do I glow when the player holding me collects a damage power-up. These low-level problems are typically in the domain of engine programming. All the core technology.
Yeah, basically what Blueprint does is kind of removes from consideration some amount of lower level, so you can kind of focus more on the abstract level. Blueprint is probably like in here maybe. So you don't have to deal with like some crazy memory management. Of course, less control means less flexibility, so there is stuff that you maybe want to touch on and you can't. But then you don't have to deal with all of this, which can get very technical and you can spend a lot of time like doing random stuff.
Technology that allows us to build a game without being too concerned with what kind of game we're making. When we start building on that core technology to solve problems that are fundamental to the specific game we're making, and building the systems that make our game playable, then we get into game programming. And then there's the work of building upon those systems to flesh out the player's minute-to-minute experience, which we could broadly label as scripting. Scripting focuses on higher-level problems, like overall flow and progression of the game.
Oh, so he would put blueprints actually in here. From his graph, I understood like higher level in here is more like game design, which blueprints are really not game design. They're still like game programming. The only thing is like, wait, can I do this? Okay, C++ is like, the domain of C++ is probably like this, and blueprints are probably like this. I don't think I would put scripting in here, unless he means like game design is then somewhere in here. But yeah.
High-level interactions between different game objects, and how specific concrete game objects look, feel, and behave. These three broad categories can help us to understand the rough division of labor in a game project, but they are generalizations. In particular, our definition of scripting casts a pretty wide net. Depending on the project and the team, there may be an actual job role called scripter, or different so-called scripting responsibilities might be divided amongst game designers, level designers, programmers, technical...
Yeah, so right now I think the role that kind of I would go mostly in might be like technical artist, gameplay programmer, but for Unreal you don't have like gameplay programmer for blueprints. It's usually going to be like C++ / blueprints or something like that. Like you don't have like solo, yeah. It's not like divided yet, but I can see companies starting to kind of divide, where you can be like blueprint only gameplay programmer, but it's still kind of in early stages.
Artists and others. Similarly, what we're calling game programming and engine programming could involve a number of different subdisciplines and job roles with plenty of potential overlap. The important point is that when we're talking about the work that goes into implementing some piece of functionality at some level, we can usually draw a distinction between programming and scripting. Usually, programming refers to solving the lower-level problems, whereas scripting refers to fleshing out the higher-level details. If you're with me so far, then we can get back to talking about C++.
Okay, I can agree with this. Yeah, sure. That's why I was confused when he said like game programming is like in the middle and then you have engine programming and then scripting in here. Scripting does give you flexibility to go very high level, but I would say it also goes a bit lower where you can like manage what types of functions you use, variables, if the variables are like serialized or something. Like there is some lower level. You're not dealing with like bytes or something, so you never go like below this line or somewhere. You're usually like in here, but you can still go low.
And Blueprints in the context of Unreal game programming. C++ is a programming language, and Blueprints is a scripting system. C++ is naturally better suited for implementing low-level game systems, and Blueprints is naturally better suited for defining high-level behaviors and interactions, and for integrating assets and fine-tuning cosmetic details. For a typical game dev project with a traditional team, C++ and Blueprints are typically used along those lines. But one of the most fundamental things you should understand about Blueprints and about Unreal Engine as a whole...
One thing, I don't know what he's gonna say, but just for this line, how I see it right now. So like 5 or 6 years ago, for indie teams, I would see it like this. And then for like AAA teams that are using Unreal, you're probably gonna use C++ like this much. And then you might use Blueprints for like 10 to 20% of things. But I think what's happening now, since they're kind of a bit more powerful right now, for indie teams, you're probably going to use Blueprints like this. Like you're going to use it for like 90% of things. And then you're going to use C++ for like few things that you don't have access to. But for bigger teams, you might use it like, I can see it like something like this more. Like maybe 60% of Blueprints you're going to use. And then 40% C++. And then if the company really wants to optimize, I can see it going like this. Maybe like 30% Blueprint, 70% C++ or something. But yeah. But I think they are decently powerful, where to go like full C++ is if you have contained project that you just want to fully optimize and you just transfer everything to C++. You want to get every bit of performance and customization that you want, basically. There is a nice balance with Blueprints, where now for like most indie or small teams, like 80 to 90% of Blueprints I can totally see.
Is that Unreal Engine does not draw this line for you. It doesn't preordain that a certain class of problems is in the domain of programming or scripting and require you to use C++ or Blueprints to solve those problems. You get to draw that line yourself. You can draw it in different places for different systems. You can lean heavily on Blueprints for prototyping and then shift the line towards C++ once your design becomes clearer. If you're a hobbyist or a student, or you're working with a small team from a non-game dev background, you can favor Blueprints as you learn the ropes.
Yes. Not even as you learn, he's gonna say as you learn the ropes. But I think in general, for finished projects, like if you spend like a year making a game and it's mostly Blueprints, like you don't want to spend another 6 months converting it to C++ and doing some crazy optimizations to get like 10 FPS performance increase. Usually you would just maybe do a month or two of optimizations, maybe some C++, but mostly just still in Blueprints. If you're indie, of course. If you're like bigger company, you have resources, just throw in C++. But yeah, for smaller teams, probably still stay with Blueprints, but optimize. There is a lot of optimizations that I can see in projects where it's unnecessary to go to C++ to get some major performance. You can still do it in Blueprints, where you might haven't been paying attention if you're using like thread safe functions, or you're doing some unnecessary casts, or you're doing like bunch of like there is a lot of small things that you can still stay in Blueprints and optimize. You don't have to jump to C++ right away when you see some hiccups in your game.
And gradually branch out to C++ as you learn more about how and when to use it. Unreal Engine is explicitly designed to offer this kind of flexibility. There's no separate scripting API. Whether you're using C++ or Blueprints, you're making use of the same underlying engine systems in much the same way. C++ and Blueprints are integrated to allow for easy interoperability, so your game can easily jump back and forth between native code and script. And Unreal extends C++ with Unreal Header Tool code generation tied into the UObject system. So it's easier than you might think to move from Blueprints to implementing higher level functionality in C++. So if somebody asks you, which is better, C++ or Blueprints? Hopefully you know why that's kind of a silly question. Of course, there are substantial differences that might motivate you to go with one or the other depending on what you're working on. So let's talk about some of those.
Yeah. So I think for this, if we are just talking about should you go like 80-90% C++ or 80-90% Blueprints, depends. Like if you're here is like one game that I don't think I would want to try with Blueprints. Like if I was recreating Minecraft or something like that in Unreal, I'm sure you heard about game 7 Days to Die, which is like mainly everything is voxels. So some games like that where heavy optimization is necessary for just the game to work, and there is like hyper specific. It's not like a third person casual RPG or something. It's like a game that has like every block is an object and you have to somehow optimize everything and it needs to work, and there is like connections. If you destroy this block then the tree falls or some crazy stuff. I think all of that is like too specific for blueprints. I think something like that I would just say fuck it, I'm just gonna do C++ for 90% of it.
Those differences. Before we go much further, I should make it clear that we're talking about gameplay programming here. In the wider context of developing an Unreal project, there are plenty of cases where blueprints are not a suitable option, simply because blueprints are designed primarily for writing game code. The exact boundaries may be a little bit fuzzy.
Yeah, this is also true. If you're like trying to do some custom solution for like multiplayer, like this doesn't even make sense to do with blueprints. Blueprints are like pre-made solutions for you to use. So yeah.
But for example, if you're talking about adding new modes to the editor, developing standalone tools, integrating external libraries, adding custom rendering code, and plenty of other similar things, then you're going to be using C++ or another general purpose language, and typically in a way that's not quite as on rails as higher level game code. The game code that we're talking about in this video, roughly speaking, is anything that deals with UObject classes. Basically anywhere you see uClass, uProperty, or uFunction macros being used. So in cases where C++ and blueprints are both viable options, there are several considerations that might lead you to use one over the other. One factor that's often cited is performance, and I'd like to start there because it gives us a chance to look under the hood and see how things really work at runtime. When you write a function in C++, you end up with plain text in a CPP file. When you write a function in blueprints, you end up with an event graph consisting of a...
Okay, so now I have a general idea how this works. I'm interested if he's gonna talk basically about execution and virtual machine and all that stuff, so I can see actually if I'm correct or not about understanding how the nodes work. So we're gonna see.
A bunch of nodes that's stored in a blueprint asset. When you build your project from source, your C++ function gets compiled to machine code. It becomes a flat listing of processor instructions that run directly on the CPU. Your blueprint function gets compiled too, but not to machine code. Blueprint functions are run through a script compiler, which flattens your two-dimensional graph into a one-dimensional listing of script bytecode. This is a portable intermediate form of your function that the engine's script VM executes at runtime. We saw this function earlier in our weapon example. It runs a line trace into the scene, and if it hits an actor, it applies damage to that actor. Let's step through the two versions of this function, one compiled from C++ and the other compiled from a blueprint, and see what we see. The function takes two parameters, a transform that gives us the starting point and direction of the trace, and the maximum distance for the trace. The machine code compiled from our C++ source is shown on the left.
Okay, that looks... Wait, so this is just an empty function, right?
The machine code...
So this is set up a frame, okay. So I'm assuming this is just an empty function. He's not going to show all of the nodes.
Compiled from our C++ source is shown on the left. As we get into the body of our function, the first thing we do is figure out the starting location for the trace. And here we see the resulting machine code. A computer's CPU works by loading data into registers and running instructions that operate on those registers. We write our C++ code using local variables and function calls, but the compiler is free to optimize those details away, so long as it can guarantee the same end result. So our machine code can look quite alien. Here, the CPU loads some data into vector registers based on how it'll need to use those values later. On the right, we can see the script bytecode generated.
So how do you kind of check the performance of this? Is the performance just how many lines the compiler needs to read through? Is that kind of how you choose, or you choose the length of it? I'm not sure how you actually do this. Because I guess both are a bit increased.
Generated from our blueprint function. and it's more recognizable as a translation of our original event graph. We can see a better example if we move on to computing the endpoint for the trace. Here, the C++ compiler has inlined all the relevant vector math. In other words, we don't end up calling getUnitAxis or the vector multiply or addition functions, which would involve passing arguments and jumping to different parts of the code. When our function gets called, the CPU just does all this math directly in a single shot. Our script bytecode isn't quite so low level. The script VM is sort of like a CPU that's implemented in software, but its job is simply to keep track of script execution, resolve expressions to values, and jump around to execute the right functions with the right arguments. When blueprints do actual work, they ultimately call down into native functions compiled from C++. So if we need to construct a vector based on our
Okay, so these are just calls of specific functions in C++, so then you have to first execute all of these lines, and these lines execute the actual code of C++. I think that's kind of general idea.
Variable. We put a make vector call in our event graph. In the resulting bytecode, the script VM prepares a local variable to hold the resulting value, and then it calls the make vector function. That function takes 3 values as arguments, so it pushes our trace distance value, along with 2 zeros, onto the script stack. Make vector is implemented in C++, so it gets compiled to a handful of CPU instructions. But since make vector is a blueprint callable function, Unreal Header Tool generates an extra function called exec make vector that bridges the gap between the script VM and native code. This is what the script VM actually jumps to, and if we expand it a bit, we can see that it pops our 3 argument values off the script stack, and then calls the actual make vector implementation, and stashes the result at the address provided by the script VM. We can continue to see this theme as we move through our 2 implementations of this function. When we actually run the line trace, both implementations end up running the same native function, but the version on the left can call that function directly, while the version on the right has to pass a bunch of data from the script VM to a native helper function that then calls the actual line trace function. When we check for a valid actor in the hit result, the native function is extremely straightforward, whereas the script function for a valid actor...
Oh, this is why... Okay, this makes sense. So I just know, just by experience, that that is valid and checks take are a bit more expensive, but I can see here why. So it has
actor in the hit result, the native function...
Like, this is crazy.
...is extremely straightforward, whereas the script function has to do more work. Computing the shot direction is fully inlined in the native function, but the script function calls a helper function. Keep in mind, though, context matters. In fact, when it comes to optimization, context is everything. Our script function has a little bit of overhead in the script VM, and then it jumps to exec getDirection unit vector, which is compiled to this bit of machine code. That function calls some other functions, and then eventually it calls the actual getDirection unit vector. So yes, the blueprint function results in more CPU instructions being run, and so it takes more time to do the same work. But if this blueprint code is running once per frame, and you have 16 milliseconds in a frame, then that overhead is absolutely insignificant. But if you had, say, 1,000 actors running this code every frame, then the overhead might start to add up. Context matters. You can't just look at this example in isolation and draw any useful conclusions. But more on that in a second. We finish our function by applying point damage if we hit an actor, and then we clean up and return. So what have we learned about performance? Well, if you have 2 equivalent functions, one written in C++ and the other written in blueprints, the C++ function is going to be faster. The C++ function can be fully optimized at the CPU level, and it doesn't incur any overhead from script execution. Incidentally, avoiding that overhead is what blueprint nativization is all about.
Yeah, I remember this. They deprecated this, but I think they are now in Unreal, basically behind the scenes. I think they are trying to optimize your blueprint code. So I think when you package or when you build your game, it will try to nativize your blueprints. I'm not sure, but I think this is the reason why when you play in the editor, the game might be way slower than when you actually play it when it's packaged and built. because it gets nativized, so gets some performance boost from blueprints.
If you enable nativization, then instead of generating script bytecode, the script compiler will spit out C++ source, which can be compiled directly to machine code. That generated source isn't meant to be human readable or editable, but it results in all the same native function calls without needing to run on the script VM.
I'm not sure if he's going to talk about how much actual performance boost, because what he showed right now before, like the speed of C++ would be like this, while blueprints on average are going to be like this maybe. Like there's going to be like 2 to 5x difference or 10x difference in general. But I think when it gets nativized, this jumps to probably like this or something. So blueprints get some performance, but of course you cannot compete with C++ if blueprints are literally created in C++.